What we found is that it is possible to detect the detailed chemical signature of a Sun-like star having ingested Earth-like planets, in fact, many of them. And not only can we detect that signature, but really for the first time we've demonstrated that the signature that we detect in detail matches the signature that we would predict should be present if planets, rocky planets like the Earth, were swallowed up in large numbers by a star like the Sun. With respect to searching for Earth-like planets, one of the things that our work suggests is that what we might be able to do is to analyze the chemical imprint that we see in the light spectrum of a star in order to better predict whether that star is likely to even have rocky planets around it or whether it has already ingested them. At the same time, what our work suggests is that the broader question that we've been trying to answer for several decades now of how often do stars like the Sun form planets like the Earth? How common are Earth-like worlds around Sun-like stars? In a sense, our work suggests that that's sort of the wrong question. Rather, the more relevant question may be, of all of the rocky planets that a Sun-like star makes, how many of them actually survive as opposed to diving into the host star? An important thing to understand is that while we have found in relative abundance what we call hot Jupiters, massive Jupiter-like planets orbiting very close to their host stars, we have found lots and lots of those. That tendency to find lots of such planets is at least in part driven by the fact that those are relatively easy planets to find. If you have a large planet orbiting close to its host star, that planet is going to tug on its host star more strongly. It's also more likely to pass directly in front of its host star so that we can detect it. And so we still don't have really robust statistics on whether those hot Jupiters are the rule or if they are in fact the exception, as is the case in our own solar system, where the massive planets, the big Jupiter-like planets, are safely far away from the inner regions of the solar system. But if it turns out that solar systems most of the time have their massive Jupiter stars in close to the host star, then that probably will indicate that rocky planets are less likely to survive the solar system formation process.
When we look at the chemical abundances of stars in binary systems, so two stars orbiting each other, where at least one of those stars hosts a planet. And the reason why binary stars was important is because since the two stars are binary, since they're orbiting each other, we know that they most likely form from the same material at the same time. So we have these two stars, they're basically twins, they form from the same material at the same time. If one of them hosts a planet and the other one doesn't, or if the architectures of their planetary systems are different, then if we see some difference in their chemical compositions, since we would expect them to be the same since they're basically twins, if we see some difference in their chemical composition, then that is most likely related to the planet formation process. Currently, we think that the Sun accreted very little amount of rocky material. Otherwise, we wouldn't see the rocky planets that we do see in our system. But it's a good question because what we're really measuring with these two stars in this binary is how much more of the material they accreted relative to the Sun. To form a Jupiter-like planet, you start out with a rocky core, and then once that rocky core gets large enough, it starts accreting a lot of gas from the surrounding disk. And so the more material, the more rocky material you have available, the faster you can get to that Jupiter size, because the faster you build up core, the faster it can start accreting a lot of gas.